take it out. Because basically, it says, how high of a hill do we need in order to get a loop of radius equals r, right? That's what we're giving you. If you want to put a number in for the radius, you can, but it doesn't change how we do step C. Okay, so we're saying we've got a roller coaster, something like this, right? We want to know what height do we need in order to make a loop of radius r, right? Now, little note on here is we're talking about a perfect sphere. We're talking about r, radius r, which means the height is actually 2 times the radius, right? And then we'll call this one h1. So we want to find h1, right? Given h2 is 2r. Okay, so energy. Let's backtrack a little bit. Backtrack from all this crap. Forget about the loop for now, and let's talk energy. We're saying that at the top of this hill, this thing's stationary, right? So if it's stationary up here, it has only GPE, right? We're in agreement on that. Okay, I'm going to call that GPE1. You'll see why in a second. So now, doop, 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 we go down at the bottom, which we're not here yet. So this isn't pertinent to part A, but at the bottom, it's only KE, right? Just making a note of that, and then we're going to ignore it for a second. I want to know here, though. So, doop, doop, doop. Uh-oh, now we're gaining some GPE. And we also have, because we're trying to make the loop, KE, right? And assuming no friction, which we are, the amount of energy here has to equal the amount of energy here. That's that law of conservation of energy thing we talked about, right? So what's our baseline equation? GPE1 equals GPE2 plus KE, right? That's our baseline equation, okay? And what are we trying to find? We're trying to find the height. So we're trying to find h1, which sits in here, right? Now, here's our basic equation, right? Plug in our stuff. What does it look like? Well, it looks like this. GPEs, we've got mg h1. That's at the start, right? Equals m, still the same mass, right? Still the same roller coaster. h2 plus 1/2 mv squared, right? We're looking for h1. We know h2. We have m and g. We're assuming we know mass and gravity, which we'll show you here in a little bit. Something, but now here's where the trick comes in. We know, we talked about before, to make a loop, the normal force at the top of the loop is going to be the centripetal force, right, minus the weight. Correct? We talked about that. That's the new stuff we talked about the other day, right? The normal force equals the centripetal force, which is the force from going around the loop, minus the weight, which is pulling down away from the loop, right? And the point at which we fall is when n equals 0, right? When n equals 0, we know that these two have to be equal to each other, right? And so if I need to find the speed necessary, to traverse that loop, right? M's cancel, gr equals v squared, so square root gr equals the speed necessary to, the minimum speed necessary to traverse the loop, right? That's the speed at which we first lose contact. So we're going to call that our minimum speed, right? Any greater than that, we make it. Okay, so that's my v, right? That's my v. It makes this equation. Okay, and if you want, m, that can go down, right? We get, let's slide this down a shade, gh1 equals gh2 plus 1/2 v, our new v over here, right? Square root gr squared. What happens? Square root and squared go away, right? So now we have a G in every term, right? So G goes away, G goes away, G goes away. We get H1 equals H2 plus 1/2 R. Well, what do we know about H2 up here? Okay, the second height is 2 radiuses high because it's a circle, right? This is a circle, so 2 radiuses is going to be the total height. So this becomes 2R plus 0.5R, which is 2.5R. That's my initial height. That's the minimum height that that hill needs to be in order to traverse the loop. Okay? So, all we did here, we took our conservation law. The total energy at the start has to equal the total energy here. This is GPE, this is GPE plus KE, right? Simple enough. We plugged in our equations, right? Which we always do. Then we took the fact that H2 is 2R, 2 radius is high, right? We plugged in this is our new trick. This is the trick that we have to remember. Plug that in for V and solved. Okay? If we would have given you an R, if you want to, if I don't give you an R, you could put an R in there. You could put 10 in there, right? What are we going to get? We're going to get 25. Okay? Well, that's just 2.5 times the radius. So you can always plug numbers in if I don't give them to you, right? But I've warned you about this, that starting the last couple chapters, the numbers go away. Okay? All right, so part B for this thing, we asked you for the kinetic energy at the bottom, right? What's the kinetic energy at the bottom? Well, here's my height, right? The kinetic energy at the bottom of the hill is an easier equation. All we're saying then is GPE, the first GPE equals KE, right? We're not talking about the loop at all. So mgh equals 1/2 mv squared. All we're looking for is the speed at the bottom of the hill, right? So mass cancels. Divide by 1/2, which is the same as multiplying by 2. 2gh equals v squared. Right? Is your v. Well, what do we plug in for height? Plug that in for height, right? So square root 2 times 2.5, right? Times g times r. To clean it up, we get square root 5 gr, right? We don't care what, remember our order of when all these are multiplied, we don't care what we multiply first. So 2 times 2.5, square root 5 gr. Simple enough. Again, it comes down to law of conservation of energy. Plug in your stuff, put in any quantities you know, and solve for the variable, right? So I'm hoping, and I know some of you are, I'm hoping more of you are starting to see why this chapter is fairly simple compared to what we've been doing. Okay? The actual physics involved is right here. Figure out the law of conservation of energy. After that, we're just substituting in equations and solving the problem, right? So less physics, more problem solving in this chapter. If you have questions, email me. We will talk to you. I don't have you guys on Thursday, so I will see you guys Friday bright and early.